ordinary pencil lead holds extraordinary properties when shaved down to layers as thin as an atom. A single atom-thin sheet of graphite, known as graphene, is just a tiny fraction of the width of a human hair. Under a microscope, the material resembles a chicken wire of carbon atoms linked in a hexagonal lattice. Despite its wave-like proportions, scientists have found over the years that graphene is exceptionally strong, and when the material is stacked and twisted in specific contortions, it can take on surprising electronic behavior. Now, MIT physicists have discovered another surprising property in graphene. When stacked in 5 layers in a rhombohedral pattern, graphene takes on a very rare multiferroic state in which the material exhibits both unconventional magnetism and an exotic type of electronic behavior which the team has coined Ferro-valleytricity. The discovery could help engineers design ultra-low power, high-capacity data storage devices for classical and quantum computers. The researcher says having multiferroic properties in one material means that if it could save energy and time to write a magnetic hard drive, you could also store double the amount of information compared to conventional devices. The research team reports their discovery in Nature. A ferroic material is one that displays some coordinated behavior in its electric, magnetic, or structural properties. A magnet is a common example of a ferroic material. Its electrons can coordinate to spin in the same direction without an external magnetic field. As a result, the magnet points to a preferred direction in space spontaneously. Other materials can be ferroic through different means, but only a handful have been found to be multiferroic, a rare state in which multiple properties can coordinate to exhibit multiple preferred states. In conventional multiferroics, it would be as if, in addition to the magnet pointing toward one direction, the electric charge also shifts in a direction that is independent from the magnetic direction. Multiferroic materials are of interest for electronics because they could potentially increase the speed and lower the energy cost of hard drives. Magnetic hard drives store data in the form of magnetic domains, essentially microscopic magnets that are read as either a 1 or a 0 depending on their magnetic orientation. The magnets are switched by an electric current which consumes a lot of energy and cannot operate quickly. If a storage device could be made with multiferroic materials, the domains could be switched by a faster, much lower power electric field. The researchers were curious about whether multiferroic behavior would emerge in graphene. The material's extremely thin structure is a unique environment in which researchers have discovered otherwise hidden quantum interactions. In particular, the researcher wondered whether graphene would display multiferroic coordinated behavior among its electrons when arranged under certain conditions and configurations. The team carried out some simple calculations and found that some coordinated behavior among electrons should emerge in a structure of 5 graphene layers stacked together in a rhombohedral pattern. Think of 5 chicken wire fences stacked and slightly shifted such that, viewed from the top, the structure would resemble a pattern of diamonds. In 5 layers, electrons happen to be in a lattice environment where they move very slowly, so they can interact with other electrons effectively. That is, when electron correlation effects start to dominate, and they can start to coordinate into certain preferred ferroic orders. The researchers then went into the lab to see whether they could actually observe multiferroic behavior in 5-layer graphene. In their experiments, they started with a small block of graphite from which they carefully exfoliated individual flakes. They used optical techniques to examine each flake, looking specifically for 5-layer flakes arranged naturally in a rhombohedral pattern. The team isolated several 5-layer flakes and studied them at temperatures just above absolute zero. In such ultra-cold conditions, all other effects such as thermally induced disorders within graphene should be dampened, allowing interactions between electrons to emerge. The researchers measured electrons' response to an electric field and a magnetic field and found that indeed two ferroic orders or sets of coordinated behaviors emerged. The first ferroic property was an unconventional magnetism. The electrons coordinated their orbital motion like planets circling in the same direction. In conventional magnets, electrons coordinate their spin, rotating in the same direction while staying relatively fixed in space. The second ferroic property had to do with graphene's electronic valley. In every conductive material, there are certain energy levels that electrons can occupy. A valley represents the lowest energy state that an electron can naturally settle. As it turns out, there are two possible valleys in graphene. Normally, electrons have no preference for either valley and settle equally into both. But in 5-layer graphene, the team found that the electrons began to coordinate and preferred to settle in one valley over the other. This second coordinated behavior indicated a ferroic property that, combined with the electrons' unconventional magnetism, gave the structure a rare multiferroic state. The researcher says that it is the first time they have seen a ferro-valleytronics and also the first time they have seen a coexistence of ferro-valleytronics with unconventional ferromagnet. The team showed they could control both ferroic properties using an electric field. They envisioned that if engineers can incorporate 5-layer graphene or similar multiferroic materials into a memory chip, they could, in principle, use the same low-power electric field to manipulate the material's electrons in two ways rather than one, and effectively double the data that could be stored on a chip compared to conventional multiferroics. While that vision is far from practical realization, the team's results break new ground in the search for better, more efficient electronic, magnetic, and valleytronic devices.